In this talk, I'm going to explain how to perform experiment 2 on solution calorimetry. So what you're going to need to do before you come to laboratory is print out a hard copy of the experiment and bring that hard copy to the laboratory along with your goggles. I will not provide extra copies of the lab for you, and I won't supply goggles, so if you don't have them, you're going to have to leave the lab and come back and probably work alone. You're going to be using the LabQuest to collect data and perform computations. For that, you're going to need the temperature probe. You've been assigned a partner and specific chemical reactions to run. Either myself or the grad assistant will use a seating chart to seat you in the laboratory. You're not going to have the same partner as last lab. It's your responsibility to read and study the lab manual before performing this experiment. It's quite complicated. Again, print out and bring a hard copy of the experiment. In this PowerPoint, I haven't detailed every step of the procedures in the lab manual, so you're going to need to follow the lab manual procedure exactly. You cannot use a computer or other electronic device to access this PowerPoint or anything else during the laboratory. You need to bring a printed copy of the lab experiment, and you can bring a printed copy of this PowerPoint as well. I actually have a black and white version where there's less of a black background online that you can print out and bring. Individual lab reports. Each individual must have their own graphs and must submit their own lab reports. So you're going to submit your lab report along with 2 graphs to me or the GA before you leave lab. For the graphs, we want you to print them out using the LabQuest and staple them to your report. However, if you can't get the Wi-Fi to work on the LabQuest, then you can get our permission, okay, to take a snapshot or scan of your, screen on your LabQuest and upload that to Canvas. I'll have it up there, but you've got to have permission before you do that. Otherwise, I'll deduct points, and Canvas will not accept all picture formats. It doesn't accept the iPhone picture format, so you'll have to probably scan it and convert it to a PDF with one of the scan programs that you've used before, like Genius Scan. All right, so you need to print this PowerPoint out, and take notes on the PowerPoint and on your lab manual procedure to be able to do this laboratory. The calculations for the laboratory are exactly like the ones you did in the pre-lab. So you can bring a copy of my pre-lab calculations if you like, or your own pre-lab calculations. I have a PowerPoint up there on Canvas on how to perform those pre-lab computations. Safety. Number 1, wear goggles. 2, you're going to work with acids and bases that they can burn your skin. If you get any on your skin, you need to rinse your skin off with water right away and let us know. You can dispose of all the liquid chemicals down the drain, but you should turn on the tap water first to kind of flood the system to dilute the acid and bases before they go down the drain. No solids in waste baskets or in sinks. And again, before you leave, you should wash your hands. All right, purpose. There's 2 parts to the experiment. Part 1 is determining the heat of neutralization of an acid-base reaction. What makes this complicated is that there are 2 different acids, either hydrochloric acid HCl or nitric acid HNO3. And they're going to be reactive with the same base, ammonium hydroxide. So we're going to assign you which acid and base to use, okay? But what's super important is if you use hydrochloric acid for the Part A experiment, then you've got to use the ammonium chloride solid, a white solid, for Part B. If you mix it up with ammonium nitrate, your results aren't going to work out at all. So you have to pair up the hydrochloric acid for Part A with the ammonium chloride for Part B. Notice that they both have the same chloride counter ion. And that's going to be given to you with the seating chart. All right. The other option that some of you will have is to perform part A using nitric acid and ammonium hydroxide. And if you do that for part A, then for part B, you're going to use ammonium nitrate solid and water. Notice that this time nitrate is the same counter ion. All right, so then I've written them out again here. Hydrochloric acid and ammonium hydroxide for part A, ammonium chloride and water for part B, or nitric acid and ammonium hydroxide for part A, ammonium nitrate and water for part B. Don't mix them up, okay? Now, in the laboratory, you're going to see molar concentrations on the bottles that contain all of these acids and bases, and they're going to be close to 1 molar, but you should write exactly what those molarities are, okay, on your lab data sheet. So they're going to be close to 1, but not exactly. One should be higher than the other. You need to write the exact concentrations with as many digits as are given on the bottle. Record that on your data sheet. For part 2, you're using solids. Ammonium chloride is a white solid. Ammonium nitrate is a white solid. You're going to be massing out about 5 grams of each of these and dissolving in water. All right, so then here's an example of what your seating chart is going to look like. Okay, so this is for room 211. And if you look at this, you'll see the doors here on the left and the fume hoods a little bit further down on the left. So this is what I'm showing here is the first bench closest to the window to the door. The students in this first bench are going to be using hydrochloric acid for part A and ammonium chloride solid for part B. On the other side of the bench, they're going to be using nitric acid for part A and ammonium nitrate for part B, so on and so forth down the different benches. And we'll post this. And if you have a question, if you forget which one you're assigned, you can ask us and we'll let you know. It's important that you pair up the HCl and the ammonium chloride or the nitric acid and the ammonium nitrate. General instructions. In the next slide is embedded a video that demonstrates how to use Logger Pro for this laboratory. You can view the video, and you're going to analyze your individualized data collected in the laboratory in the same way as in the video. Now, I already had this video in the pre-lab PowerPoint, so I'm not going to show it again, but here it is, since I have this PowerPoint up there. If you click on this graph, you'll see a little arrow here that'll start the video. And then the instructions that go along with those computer demonstrations, steps 12 and 13 of the lab manual. Okay, so in this laboratory, when you turn in your lab report before the end of lab, you have to write some balanced chemical equations. And all those balanced equations have to be written as molecular equations, not ionic equations, like nothing like ammonium, nothing like hydroxide, nothing like chloride, nothing like H+, no ions in any of your chemical reactions. But what's also important, aside from using molecular equations, is that you show phases along with the reactants and products. Most of them are going to be in the aqueous phase. Water is really the only one that's going to be in the liquid phase. And the salts, the ammonium chloride and the ammonium nitrate, are going to be in the solid phase. This is really an illustration of what's happening in this reaction. When you mix the acid and the base, you get some products. I'll just write P, plus heat is being released. So when we put energy versus reaction coordinate reactants to products, since the reactants are losing heat to the surroundings, the products have less energy. So the change in energy, we call it delta H, is going to be a negative number. So you're going to see a temperature rise indicating that heat is moving from the reaction to the surrounding water and the calorimeter cup. So for part A, remember you're doing an acid plus ammonium hydroxide. The general reaction is, as you learned in Gen Chem 1, acid plus base always gives a salt plus water and heat, which we're going to measure. We call this the heat of neutralization. Since heat is being released, this is an exothermic reaction. Exo from the word exit, meaning out. Energy or heat is coming out of the reaction. All right, so here are more specifics. These are the chemical equations that you're going to need to write on your lab report form for whether you're assigned the nitric acid and ammonium hydroxide or hydrochloric acid and ammonium hydroxide. And notice that these are all written as molecular equations. So when we react these together, the H from the acid combines with the OH from the base to form water, and the positive ammonium ion reacts with the negative nitrate ion to form ammonium nitrate. Notice I have the phases here. Or for part A, you're doing the hydrochloric ammonium hydroxide reaction. Again, the H plus from the acid reacts with OH from the base to form water. The chloride and the ammonium come together to form ammonium chloride. So this is the apparatus. You're going to use a T probe, a temperature probe. It connects over here to the LabQuest, and this is not a very good picture, but it's a picture of a LabQuest, the newer version. You're going to use styrofoam cups, but you're going to take two of them. You're going to put one in the other. Okay? Don't throw them away at the end of the experiment. Instead, rinse them with the eye water and leave them out for the next group to use. They may be on your benches, or there may be an area in the lab to put them. I'm not sure what they've done yet. So again, this is an exothermic reaction. Our system is the chemical reaction that we're running, the acid plus the base forming salt water and generating heat. So this is a schematic of your calorimeter. Double nested calorimeters. You're going to have a cardboard top to this thing with a hole in it. The T probe goes in the hole. Your reactants, 50 mils of acid and base, are in here. As the reaction happens, the heat passes from the solution to the calorimeter walls, to the water, and to the T probe, and the temperature should go up for this acid-base reaction. You're going to use a 50 mil grad cylinder to measure volumes of acids and bases, but you need to report your volumes to 0.1 mils. They don't need to be measured at 50.0 mils exactly. You could put in 49.8 mils or even 49.5 mils. I wouldn't go below that. But you don't have to measure exactly 50 mils, but you have to record how many mils you put into your calorimeter cup. And it has to be measured to 1 decimal place. So they say it doesn't necessarily have to be the acid that you measure first. Okay, so in the procedure it says measure the limiting reactant first, 50 mils of it. The limiting reactant is the one that has the lower molarity. So that's when you measure 50 mils of it, you put it into the calorimeter. You start your LabQuest temperature versus time. It tells you how to set that up. And with just that reactant, just one reactant sitting in there, the temperature should be constant. You want to let it run for a little while to get that initial temperature. Then you add the other reactant, 50 mils, and the temperature should shoot up and then kind of level off like that, like you did in the pre-lab. Okay, so again, the acid plus the base, when they react, emit or cause heat to flow from the reactants to the surroundings. So I have an arrow going out of this system to the surroundings. We call that amount of heat QCAL for calorimeter. Here's a convention in thermodynamics, which we haven't done yet in the course. Heat loss is always a negative number. Heat gain of anything is always a positive number. So with that convention, the surroundings, the cup, the calorimeter cup, the probe, and water, they're gaining heat because heat is moving from the reactants to the outside. In the system, the reactants are losing heat. So since heat loss is always a negative and heat gain is a positive, these numbers should be equal in magnitude. But one is negative, the other is positive, to actually make them equal to each other, we tack on this negative sign because the negative of a negative is a positive. So negative the heat lost by the chemical reaction equals the heat gained by the water plus the heat gained by the calorimeter. But I think whoever wrote this experiment decided not to take the calorimeter into account. So that's not part of the calculations. So this is the equation we'll get. This is the heat lost by the system, which you're interested in measuring. And that's equal to the negative of the heat gain of the calorimeter. We could have written this here in a positive to match it up with this equation here. All right, so then when you perform that reaction, you'll have initially a constant temperature with just one reactant sitting in the calorimeter. At this point here, you add the second reactant, and the temperature goes up, and then it kind of levels off. And you're going to use that analyze, interpolate menu on the lab quest to find this final temperature here. And then the difference between the final temperature and the initial temperatures is the delta T for the experiment, which you're going to actually record. Okay. Now, when you run this first reaction, before you go to the second reaction, you need to make a printout of this. You need a printout for reaction A and reaction B. So make the printout right away so that we have the data, or even take a snapshot in case you lose the printout later on. But you need to have these graphs. How to tell the limiting reactant, that's going to be the one with the smaller molarity, but you can actually count the number of mole, you can actually compute the number of moles of reactants, each of the two reactants, the ammonium hydroxide and the acid, using this equation, which you did in pre-lab. For part B, you're dissolving a solid salt in water. So again, using a grad cylinder, you measure 50 mils of water, okay? You begin a temperature measurement with the water in there, temperature versus time. And then you add 5 grams of either the ammonium chloride or ammonium nitrate, whichever one you've been assigned. I wrote 5.xxx because these numbers, these x's don't have to be zeros, okay? To save time, maybe this is what you measured, or maybe this is what you measured on the balance. Don't waste your time trying to get 5 grams exactly, but whatever you do measure, you've got to record on your data sheet, okay? So first you have the water sitting in the calorimeter, and then you add the salt, and the temperature is actually going to go down and then back up again. So this is going to be what's called an endothermic reaction. Because temperature is going down, the system is absorbing heat. Heat is going from the water into the system. Temperature goes down. Okay. Lab report sheets. All right, so this is part of the data sheet. You must construct a complete organized data sheet to be used for recording all data during the experiment. All right, so to do this correctly, you should read through the experiment first. You should understand what I've given you in the PowerPoint. You've got to decide what to write. We're not going to tell you, okay? We're not going to go around and check what you've written down, use non-erasable ink, but obviously the volumes, the chemical formulas, the units, okay, the masses that you use, all those things would be important. All right, so then question number 1, data analysis for reactant A or B. Remember, reaction A is HNO3 plus NH4OH, or HCl plus that. And reaction B is the solid, let's see, so ammonium nitrate. Or ammonium chloride. Okay. And so you're going to use that Lager-Perl procedure, analyze, interpolate to find the final temperature. So for reaction A, you want this temperature right here. Okay. And the difference in temperature between that and the initial temperature there to get delta T. So final temperature, initial temperature, and then subtract to get delta T. And then for reaction B, which I have down here, you want this difference in temperature. So this is initial for B, and this is final down here, where you use the interpolate, okay? You get another delta T, so you have final temperature, initial temperature, and then subtract. Don't forget to print your graph for part A before moving to graph B. You should take a photo as well. Then we go to the second question, calculation. Using the specific heat of the product solution from table 1, which is in your lab manual. And then they talk about the two reactions that you could have had. And the mass of product solution formed, compute the heat capacity of the reaction products using equations 3 for A and equation 4 for B. So I think in your lab manual, these are the wrong equations. They're going to be equations 5 and 6. And I've actually copied those equations under reaction A and reaction B. So you're computing the C, okay, using these chemical formulas. Now, you did this one in pre-lab, but you haven't done this one over here. So you need this CS value. You need these volumes V1 and V2, which are close to 50 mils, and you need the densities. They're going to be in a table. For reaction B, CS value in a table, V is close to 50, density in a table, mass, the soda is going to be close to 5 grams. Okay, we're going to look at these in more detail. All right, so let's just look at reaction A only and ignore reaction B. This is the equation that we're going to use to compute C. And again, you either have the, well, this is wrong. This is either HCl and ammonium chloride or HNO3. Copied wrong stuff there. All right, so then this is the equation that we're computing for. We're computing the C. You'll see a table in there. You know, they have too much in that table, in these tables. I mean, it makes it very complicated and hard to understand. I think they have like molarity here. Molarity. You don't need molarity for these computations, so why bother having it? So I kind of blocked that out. So what I've done here is I've shown densities for water, which is 0.997 grams per mil, HCl 1.02, nitric acid 1.03, and ammonium hydroxide 0.992. So these densities go here and here, and I'll be doing example calculations for each one. And these volumes are around 50 mils, and the CS is in a table as well. If you're doing the reaction of HCl and ammonium hydroxide to form ammonium chloride product, you're going to need the CS value of 4.04. So that's in a table. I blocked all the other stuff out. All right, so here's an example calculation using hydrochloric acid and ammonium hydroxide. There's our equation right there. The CS is for the ammonium chloride product. I'll say the V1 D1 is for HCl, the V2 D2 is for the other reactant, ammonium hydroxide. All right, so from our table, we found that CS is 4.04. So that's why I have that there. And those are the units. You should show the units in your calculations. Let's say that we use 50 mils exactly. So V1 and V2 are both 50 mils. And since HCl is the first one here, the density for the HCl was 1.02. And the density for D2, the ammonium hydroxide, going back to the table, was 0.992. So that's why I have 1.02, 0.992 here. Be careful with the arithmetic. 3 significant figures in the answer. Don't forget the units. Okay? You would lose points if you don't have the right number of sig figs or the right number of units. All right, so now we're going to look at an example of nitric acid and ammonium hydroxide. So the product here is the ammonium nitrate. It has a CS value of 4.01. That makes sense. Okay, it does. And then here's how you do the calculation. Here's the reaction. Okay, here's the formula that you calculate C with. I'll say V1 and D1 are for the nitric acid and 2 is for ammonium hydroxide. Again, we'll say we use 50 mils of each. And from the table, and actually reproduce densities down here. Let me bring that up a little bit. Okay. Make it slightly smaller. The nitric acid has a density of 1.03. There it is there. And the ammonium hydroxide, 0.992. So again, we're careful with the arithmetic. We need 3 sig figs in our answer. We need the right units. So those are the numbers that you show in these calculations here, okay, in your final answer down there. So then did that, and that. And now we're going to go to reaction B. So you should have printed off the curve for reaction A from the lab quiz. So reaction B is to compute the specific heat C when you dissolved the solid, either ammonium chloride in water or ammonium nitrate in water. And this is the equation that you're using here. My pen's not working. All right, so then for this particular reaction, again, you have to sort through all the data. You're going to need the specific heat of the ammonium chloride solid, or ammonium chloride in water, 3.93 CS. Okay, you don't need molarities, so I crossed that out. And then this is the equation that you use to calculate C for the ammonium chloride plus water reaction. So this mass should be close to 5 grams. Maybe it's 4.915 grams, which is fine. The volume should be close to 50. The density, as for the ammonium chloride salt, is 0.99. Actually, it's the density of water. This is for water here. Around 50 mils. Density of water from the table is 0.997. Using 5 grams of ammonium chloride there. And the CS for the ammonium chloride is 3.93. There it is there. So we do the arithmetic and we calculate a value for C for this reaction. This is the actual reaction that you need to write later on as a molecular equation on your lab report. So I've given it to you in advance. I won't give it to you in laboratory. Okay. All right. So then that C is, we're going to right here. You're going to show your calculation and write your C in its unit there. So there's for the first one. All right. So then the other reaction is ammonium nitrate going from solid to the aqueous phase. That's the equation that you're going to need to write in your lab report. For the ammonium nitrate, the CS value is 3.98. So then here's the setup, 3.98 here for the ammonium nitrate. This is for the water. This is for the salt, which is ammonium nitrate. Okay. Assuming 5 grams. Again, the density of water, assuming 50 mils. We go through the calculation. There it is there. And again, there's the reaction that you need to have on your lab report. For part 3, it says compute Qcal for both reactions in kilojoules, then give the value for delta H in kilojoules. All right, so they give you this here. So I think there's a mistake in there. In the lab report, I saw this equation here, but the CS should be a C there and there. Okay, so basically what you do is you take delta T, which was like question number 1. If I can find that real quick. I don't think I can. But the delta T is from the lab quest, one of the first questions. And the C is what you just calculated for reaction A. So you multiply those two numbers together. And then since this answer is in joules, you have to use this conversion factor to convert the joules to kilojoules. And then take the negative of what you calculate, because delta H is minus Qcal. So they ask for the Qcal and the units here. I'm not going to tell you what they are. And then the delta H, which is the minus of that Qcal there. And then for the other reaction, okay, the same idea. For reaction B, C times delta T. Convert to kilojoules, right, to Qcal, and the negative sign of the Qcal is delta H. You need sig figs and units. We won't tell you since I've shown you what to do. In the next question 4, it says compute the moles of limiting reactant, just like in the pre-lab. They give you some molar masses, but you only need the molar masses for reaction B, not for reaction A. Don't need the molar masses. This is how you compute number of moles, just like in the pre-lab. So you're going to have to do that for both reactants that you were assigned. And if you're doing part B, then you're going to compute the number of moles of ammonium chloride, or should be ammonium nitrate, is the mass, which would be close to 5 grams, divided by the molar mass. Okay, so it gives you the number of moles. And here they want the limiting reactant only. Then for number 5, what you do is you take the delta H from step 3, divide by the number of moles from step 4. Okay, the answer is going to be in kilojoules per mole. You write that here. Same thing for reaction B. For 6 here, write the complete balanced equations. I've already given them to you, so I'm not going to rewrite them here. I've given you the balanced equations for reactions A and B. You're only going to write the one for the one that you're assigned, either those two or these two. Then for near the end, you have to use Hess's law, which we haven't done in class. Let me illustrate what it is. Let's say that we want to find the delta H for our reaction A plus B going to D from two reactions, A plus B going to C plus D, where the delta H is 20, and E going to C, where the delta H is 10. Now, we have to add these two reactions to get this here. If we just add them up, we're not going to get it. If we add these reactions up, we get A plus B plus E going to 2C plus D. That's not what we want here. But if we reverse the second reaction, C going to E, and if we reverse it, we change this to a negative. Now, if we add these two reactions, okay, this C cancels this C, and they drop out, and we get A plus B going to D. So that's what you're going to do with the two reactions that you actually have here for A and B. You're going to add them together, but you're going to have to reverse one. Okay, so there's an example when you reverse them, because you change the sign of the reverse reaction, the delta H for what you're looking for is 10, not 30. So for number 7 then, your two reactions are going to look like this. You're going to have to add them together, but before you add them together, you're going to have to reverse the second reaction. You'll see that something cancels out, and when you add them, you'll get the reaction that you need. I showed you what to do there as well. Okay? So you'll calculate the delta H and put it here with the units. Don't forget to, make a copy of the graph for both A and B and submit them with your report due before you leave the laboratory. Okay, so I think that's going to be it for this